Any questions? All right, so let's play around with some of the stuff that we've done. So based on what we talked about yesterday, the fact that time is not constant, or it's not the same for everybody. Suppose I have a rocket that's traveling at 0.9 times the speed of sound, or speed of light, since that's the topic we're talking about, really. Question is, if the rocket is gone for a year, how much will people on Earth have aged? So the rocket goes there, comes back. I don't think I've done twin paradox with this group. Okay. All right, so it's gone for 1 year. Or I should say the people in the rocket have aged a year. Because time on the rocket is different from time on Earth, let's figure out what that time difference is, or at least the factor, and that's when this comes into play. So let's figure out gamma. Gamma is 1 over the square root of 1 minus 0.9 squared, which is you got 10?
Yes.
That doesn't sound right.
I have 2.294.
That sounds more like it. Did you square the 0.9?
Just, I made a mistake.
Okay. All right, so 2.29.
I confirm.
Yes.
Units?
Gamma is unitless?
Okay. So if 1 year passed for the people on the rocket, by the time they get back to Earth, 2.29 years have passed.
2.29 what is passed?
Years. Since this gamma itself is unitless, but I'm putting in a factor of if the proper time is 1 year, then the time on Earth would have been 2.29 years.
Right. So that's it for this problem.
Yes. Until I extend it.
Yeah, I was gonna say, this is easier than what we usually do.
All right, so from the Earth's point of view, that rocket goes away and comes back. From the rocket's point of view, the Earth goes away and comes back. So shouldn't we be able to apply the same logic from the rocket's point of view? The Earth is gone for a year at 0.9 times the speed of light. Why haven't the people on Earth aged a year and the people on the rocket aged 2.29 years?
Because the Earth isn't actually moving faster, it's just the rocket.
What
Are
is-
we traveling
What
at-
does movement mean?
It's relative.
Yeah. So why is this point of view different from this point? Why does this point of view give me a different answer than this point of view?
Because your baseline has changed, like whatever the normal or unchanged, like control versus experimental, things like it's flip-flopping.
Does Earth have a beta? Would it be?
Yeah, well, from the rocket's point of view, the Earth is traveling at 0.9. Beta would be 0.9. 0.9 times the speed of light. So in the first scenario, if you have, and this is why it's called the twin paradox, I have set of identical twins born within a minute of each other. So we'll assume the same age. And so this is Sue and this is Lou. Sue, after the trip, is 1 year older. Lou is 2.29 years older. But it seems like if that logic works, then we should be able to have logic here, and so Lou would be 1 year older, and Sue would be 2.29 years older. But only one of these can actually be true. When they come back together again, one of them will have age. It's not like, we've created two Sues and two different Lous. And matter of fact, this is the solution here. But there's something physically different between these two situations. I'm not worried about the Earth going around the sun, or the sun going around the middle of the Milky Way, or the Milky Way moving. I'm not worried about all that. Let's just simplify it down. What is physically different between Sue and Lou's experience besides the age?
Speed?
Like velocity. I'm looking at the beta, the formula that you have for beta. It's v over, what is c?
Speed of light. Roughly 3 times 10 to the 8 meters per second. But you say speed is different. They disagree, Sue and Lou disagree on what's moving at 0.9 times the speed of light, but they both agree that something's moving at 0.9 times the speed of light. And both legitimately.
It makes sense, but I just don't know how to explain it. Like, the Earth isn't going any faster than it's not going anywhere. I just don't know how to explain it.
So what do the people how's that different from the rocket? I mean, you can make an argument from a physics point of view that, take one part of your body, like your left eye has never moved your entire life. The center of your left eye. Just the world has moved around it. It is legitimate from a physics point of view to look at it that way. Not necessarily simple mathematically, but point of view should not change the physics.
Is it that the length of a year is different in these two situations?
I'm still assuming that a year is a year, that I'm not redefining time in that way.
Does it have to do with the mass of the Earth and the mass of the rocket?
No.
If you ever had a physics class, come up with the answer.
Eventually, it takes some coaxing.
Is it just the distance traveled by the rocket?
Say it again?
The distance traveled by the rocket?
The distance traveled by the rocket from the Earth's point of view is the same as the distance the Earth travels from the rocket's point of view. And the distance that the rocket travels from the rocket's point of view is the same as the distance that the Earth travels from the Earth's point of view, would be 0. All right, so you're in the rocket, you're on Earth. So imagine you've split yourself into you and your twin. What are you going to experience in the rocket?
Zero gravity?
The gravity, yeah. There's,
Assume artificial gravity. If you want to bring gravity into it, then suddenly you're bringing in general relativity, and that's a whole other
And
huge
we don't need to
pain in
make
the
this more
butt.
difficult than it is.
I was trying to bring in general relativity,
No,
but I guess Brooke
Harrison,
doesn't want
we're
to.
okay. I think we're okay, Harrison.
All right, so let's assume that they have some sort of artificial gravity on the rocket ship that people on the rocket can't tell. They're looking out the window and they see the Earth going, shooting way off. I will say that for half the trip, they're both right.
For half of the trip? That's weird.
Yep.
What do you mean they're both right?
As in, for half of the trip, from the rocket's point of view, Earth is zipping at 0.9 times the speed of light. They do the calculations about which one's aged more, and they're absolutely right.
Okay.
Down here, I guess that, whatever, I just did the rocket's point of view? Okay, so down here, from the Earth's point of view, for half the trip, they do the calculations about which group is aged more, and they are absolutely right. Why for only half the trip?
Halfway, they start to come back.
And in order to do that, what must they do?
The rocket has to turn around.
Which means what?
Oh, the velocity is changing, because they have to slow to a stop and turn around.
Special relativity deals with non-accelerating frames. So and you're sort of on it when you said the Earth doesn't move. More specifically, the Earth does not experience that force that's acting on it. The Earth is not going to accelerate. Even though it appears to be accelerating, there's no force acting on it causing it to turn around. Whereas here, a force has to act on the rocket for the rocket to turn around. And that is when you basically collapse it into this scenario. So one of the things to realize is that special relativity deals with non-acceleration. And accelerating can change things. If you want to get into accelerating, general relativity.
Harrison, it's all you.
That's me.
And if you're interested in that, there's a book by Thorne and Wheeler that I found. There's a PDF for it online. And it's basically written so that for those who are new to it, you can read sort of the first half of each chapter. And if you want to go into more detail, you read the second half of each chapter.
Have you read it cover to cover?
I have not. General relativity kicked my butt in college, in grad school. All right, so let's talk about actual experimental evidence for any of this stuff being true. And so we will talk about the Rossi-Hall experiment, 1940. And let me get the specs for it. All right, so Rossi and Hall are, I think they're MIT professors. I did not write that stuff down. Two different people. The Rossi-Hall experiment, 1940. Basically, they're looking at muon decay. The way that you look at any subatomic particle that's coming in from outer space, or from anywhere, you get a tank of superheated fluid. Actually, they probably had gas chambers that, yeah, it's still called a gas chamber. You basically get a substance in here that is the smallest disturbance would cause basically bubbles. In the bubble chambers that they have where there are liquids, you basically get superheated liquids so that you are well above the boiling point, but there's enough pressure on it to keep it suppressed. And just the tiniest little disturbance will cause bubbles, basically cause it to boil. So in that situation right there, as a particle comes through, because there's so much pressure, you do get bubbles, but it's not like you suddenly get this overflowing of bubbles. You get the series of bubbles here as the particle moves in that direction. And so you can count the number of these particles that come through. You expose it to an electric field or a magnetic field, you can see it curve. You had a master set problem with similar to this, where you expose it to a field, it will curve, and then based on that, you can have a pretty good idea what the particle is. So they were looking at muons. And because the letter mu is not used enough, we'll use it one more time. This would be the representation of a positive muon and a negative muon. So these are particles that they went up on top of a mountain, Mount Washington, which was about 1,900 meters tall, or an elevation of about 1,900 meters. And they counted the number of muons that came through in an hour. And they had 560 muons per hour. Just so you know, I put the plus here. There is a sort of tradition that even though you can see positive and negative muons, you put the plus here just to represent all the muons. If I didn't put that in any symbol in there at all, that mu could be so many other things. So you put a little plus there to indicate we're talking about a particle. Then they went down to sea level and they did the exact same experiment to see how many muons there were at the bottom. So let's figure out, let's make a prediction, assuming general relativity is, or sorry, special relativity is complete bunk. We'll do it again, assuming that there's some credibility to this, and then reveal the big answer about how many they actually saw. So they have the half-life. The half-life of a muon, so if I had a bucket full of muons, how much time would it take for half of them to basically decay? And the half-life is 1.56 microseconds. That's how long that 50% of them would die within 1.5 microseconds. These muons that are traveling through are traveling at a speed of 0.995 times the speed of light. In other words, beta is 0.995. And I'm pretty sure the 1900 and sea level, okay. So, how many of these muons would survive? If special relativity had no bearing whatsoever, how many would survive by the time they get down to the bottom? All right, well, let's figure out how much time it would take. What's the formula for speed? Average speed.
Distance divided by.
Just, yeah.
I heard distance, I assume you said time. So the time it would take for the particles to get to the bottom would be basically the distance traveled over the speed, or 1900 divided by my speed, which would be 0.995 times the speed of light. And approximation is fine for this. It's meters. And that's meters per second. And so what do we get for the time it would take for them to get to the bottom?
I got 5.7 to the 11th, but I could be wrong.
5.7 times
The 11th to the 11th.
to the 11th?
Yes.
No, that's not right.
I have 6.37 times 10 to the negative 7.
That would make more sense. 6.37,
Six. Yeah, 6.37 times 10 to the negative 6.
negative fifth,
6.
6.
I just got that too.
In other words, 6.37 microseconds. Well, if half of them are gone after 1.56 seconds, this is roughly 4 lifetimes here, or 4 half-lives. So I would expect that it would be half, 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 and half, whatever's left over. We can be more sophisticated than that, but, so basically, if we did our initial amount times 1/2 raised to the time divided by 1.56. This is the number of muons that would survive after a certain amount of time. It's basically the half-life formula. So if time is 1.56, this would be 1/2 to the first power, which is 1/2 times that, so half would be gone after 1 lifetime. So at 6.3 seconds, but this is microseconds here. After 6.37 microseconds, how many are left?
I have 559.99.
Something's off.
Yeah.
It's the 6.36 microseconds divided by 1.56 microseconds.
Yes, and then 1/2 raised to that power.
Both of those are microseconds.
I got 560, which doesn't make any sense.
All right, so we end up with 560. 560.
I've got 33.
It's about 33.
So 1/2 to the 6.37 over 1.56, that's roughly 4. So it's 1/2 to the 4th power, so this should be roughly 560 divided by 16-ish. So you got 34,
33.
33. So, if special relativity is bunk, then, or Galilean, I should say, if Galilean relativity were correct, classical mechanics were correct, then there should only be 33 muons at sea level. Now let's see what it looks like from a special relativity point of view. So these muons are traveling really fast, and so let's figure out what the Lorentz factor is. So it's 1 over the square root of 1 minus 0.995 squared. And so what is gamma? A whole lot better.
Yeah, I was gonna say I got about 10 this time, but that was wrong last time.
Yeah, with a different number this time. All right. So the time difference, or the factor time multiple, is roughly 10. So even though on Earth, that's the amount of time that would have elapsed, from the muon's point of view, it would be roughly 1/10 of that. We can get slightly more precise since it's got the 0.01 there. So the time on Earth, 6.37 microseconds, is equal to gamma, 10.01, times the proper time, the time from the muon's point of view. So 0.638, or still 37.
6.36, then wait, hold on, because it's just 6.37 microseconds divided by 10.01.
Yeah,
Yeah, I got,
0.63 repeating.
0.63 repeating, oh, 63, okay. That went the wrong direction. All right,